Right now, even if your engine feels like it's running fine, there could be a single dirty sensor silently killing power, increasing fuel consumption, and shortening engine life without triggering a single warning light on the dashboard. And that's what makes this so dangerous. How can a component no bigger than your finger make a car feel sluggish, burn more gas, and fail an emissions test all at the same time? Dealerships and independent shops across the United States see the same pattern over and over again. Spark plugs get replaced, ignition coils are swapped, fuel pumps are blamed, and thousands of dollars are wasted. The problem doesn't go away until someone finally cleans a sensor that almost nobody touches. And no, it's not the one most people are thinking about. There's a hidden culprit that slowly accumulates dirt for years, feeds false data to the ECU, and turns a perfectly healthy engine into a chronic underperformer. Throughout this video, we're going to break down the most problematic engine sensors one by one. But the one that fails the most, the one almost never cleaned, and the one that can completely transform how your engine behaves in just minutes, will only be revealed at the very end. Number 13. The MAF sensor, mass airflow. The mass airflow sensor is one of the most critical and at the same time most neglected components in modern fuel-injected engines. Its job is to measure, with extreme precision, every gram of air entering the engine. Most MAF sensors used in vehicles sold in the US rely on a hot wire design, using an ultra-thin platinum wire roughly the thickness of a human hair. This wire is electrically heated to a constant temperature, and as intake air flows across it, the air cools the wire in direct proportion to airflow speed. What the ECU is actually measuring is the amount of electrical current required to keep that wire at a stable temperature. That current value is instantly translated into air mass data, updated in milliseconds. The serious problem begins when microscopic dust particles, oil vapor from oiled aftermarket air filters, or general environmental contaminants coat that delicate wire. Once contaminated, its thermal behavior changes, and the data sent to the engine computer becomes inaccurate. The ECU now believes more or less air is entering the engine than reality, and it responds by delivering the wrong amount of fuel. The symptoms are often confusing: noticeable power loss during hard acceleration, fuel economy dropping for no obvious reason, unstable idle that comes and goes randomly, and in more severe cases, the engine stalling when coming to a stop. Diagnostic data from US repair shops shows that nearly 40% of vehicles with rich or lean mixture trouble codes have dirty MAF sensors, not failed ones. Proper cleaning requires a dedicated MAF cleaner spray and a hands-off approach that never physically touches the sensing element. But there is another air measuring sensor that works on an entirely different principle. Number 12. The MAP sensor, manifold absolute pressure. The manifold absolute pressure sensor represents an alternative strategy for calculating engine load, commonly used in speed-density fuel injection systems found in many American vehicles. Instead of measuring airflow directly, the MAP sensor measures the pressure inside the intake manifold. It uses a piezo-resistive element that changes electrical resistance in response to pressure applied to its surface. In simple terms, it converts engine load into an electrical signal. When the throttle is closed and the engine is idling, intake vacuum is high and the sensor reports low absolute pressure values, typically between 20 and 30 kilopascals. During wide-open throttle acceleration, vacuum drops and pressure rises to near atmospheric levels, around 100 kilopascals at sea level. The ECU combines this data with engine speed and intake air temperature to calculate incoming air mass using complex thermodynamic equations. The critical failure point usually isn't the sensor itself, but the vacuum source feeding it. Cracked vacuum hoses, loose fittings, or partially disconnected lines allow leaks that completely distort pressure readings. The sensor reports less vacuum than actual, making the ECU believe the engine is under heavier load than it really is. The result is excessive fuel injection, skyrocketing fuel consumption, black smoke from the exhaust, and persistent rich mixture fault codes. In real-world shop diagnostics, simply cleaning the MAP sensor port and verifying hose integrity resolves roughly 80% of issues blamed on the sensor. But there is an even more influential sensor when it comes to emissions control. Number 11. The oxygen sensor, also known as the lambda sensor. Oxygen sensors mounted in the exhaust system are the engine computer's eyes for monitoring combustion efficiency in real time. They constantly fine-tune the air-fuel mixture thousands of times per minute. Most vehicles in the US use zirconia oxygen sensors, which rely on a ceramic element heated to over 300 degrees Celsius. This element generates a voltage based on the difference in oxygen concentration between exhaust gases and outside air. When an engine runs at the ideal stoichiometric ratio of 14.7 parts air to 1 part gasoline, the sensor outputs approximately 0.45 volts. If the mixture becomes lean and oxygen content in the exhaust increases, voltage drops below 0.3 volts, signaling the ECU to add fuel. With rich mixtures, voltage rises above 0.6 volts. The major problem occurs when these sensors become contaminated by lead, silicone, or phosphorus deposits, often caused by low-quality fuel or oil burning due to worn piston rings or valve seals. These contaminants chemically poison the zirconia element, slowing its response time and reducing sensitivity. The sensor still works, but sluggishly, sending delayed signals that the ECU struggles to interpret correctly. The result is slow oscillation between rich and lean mixtures, increased fuel consumption, noticeable power loss, and almost guaranteed failure during emissions testing. However, there is still one position sensor whose failure creates a completely different set of symptoms, and that's where this story gets even more interesting. Number 10. The TPS, Throttle Position Sensor. The throttle position sensor is a precision potentiometer mounted directly on the throttle shaft, and its job is to tell the engine computer exactly how much throttle the driver is asking for at every single moment. Even though it looks simple, it's a critical component. Inside the sensor there is a circular resistive track, and a movable contact slides along that track as the throttle opens and closes. This divides the reference voltage proportionally to throttle angle, typically producing around 0.5 volts with the throttle fully closed and close to 4.5 volts at wide open throttle. What the ECU does with this information is absolutely essential. It decides whether the driver is gently accelerating, where fuel economy is the priority, or flooring it, where the engine needs enriched fuel mixtures and aggressive ignition timing for maximum power. The real problem begins when the internal resistive track starts to wear or becomes contaminated, creating dead spots. In those zones, the voltage signal briefly drops out or fluctuates unpredictably. These dead spots almost always appear at the most commonly used throttle positions, like steady highway cruising or elevated idle in stop-and-go traffic. From the driver's seat, this feels like jerky acceleration, sudden hesitation, brief power loss at very specific pedal positions, or in extreme cases, complete engine shutdown when the throttle passes through those worn areas. In professional diagnostics, technicians verify TPS health by slowly opening the throttle while watching live voltage data on a scan tool, looking for sudden drops or spikes that clearly indicate internal wear of the potentiometer. Number 9. The crankshaft position sensor. Without the crankshaft position sensor, a modern engine is literally blind. This small sensor, mounted very close to the flywheel or a toothed reluctor wheel on the crankshaft, generates perfectly timed electrical pulses every time the teeth pass by its magnetic tip. What's really happening is that the ECU uses these pulses to know the exact position of every piston at all times and the precise speed at which the engine is rotating. This information is what allows the computer to determine exactly when to inject fuel and when to fire the spark. When this sensor becomes contaminated with metallic debris, burnt oil residue, or general grime, the signal becomes distorted and intermittent failures begin to appear. The engine may shut off when hot with no warning, crank longer than normal before starting, or lose spark for fractions of a second while driving. In US repair shops, it's extremely common to see engines that appear to have serious ignition or fuel pump problems fully recover after nothing more than cleaning the sensor tip, removing metal shavings with a clean cloth, and using electrical contact cleaner. But knowing crankshaft position alone isn't enough. The computer also needs to know exactly what the camshaft is doing. Number 8. The CMP, Camshaft Position Sensor. The camshaft position sensor works together with the crankshaft sensor like two perfectly synchronized clocks. While the crank sensor tells the ECU overall engine speed and position, the camshaft sensor reveals the exact phase of the engine cycle for each cylinder. This allows precise sequential fuel injection and accurate control of variable valve timing systems. The sensor is usually mounted in the timing cover or directly on the cylinder head, reading a trigger wheel or a single metal protrusion on the camshaft. Its real job is to send one unique reference signal per camshaft revolution, identifying cylinder number 1 at its combustion stroke. When this sensor starts to fail due to oil contamination, thick sludge, or internal cracking, the ECU loses that fine reference and switches into a degraded mode. Sequential injection is abandoned in favor of batch injection. Idle quality becomes unstable, and cold starts take noticeably longer. Many engines develop mild hesitation between 2,000–3,000 revolutions per minute that gets incorrectly blamed on ignition coils or fuel injectors, when in reality a contaminated camshaft sensor is sending weak or distorted signals. A simple visual inspection and cleaning of the sensor's reading area can dramatically restore smooth operation. But there are sensors that are even more ignored, and they get dirty simply by air passing over them. Number 7. The IAT, Intake Air Temperature Sensor. The intake air temperature sensor is usually a tiny component threaded into the intake manifold or integrated into the air intake duct, so discreet that most drivers don't even know it exists. Its job sounds simple, measuring how hot or cold the air entering the engine is. But what's really happening is critical for fuel control. Cold air is denser and contains more oxygen per unit volume, while hot air is less dense. The ECU uses this sensor's data to fine-tune how much fuel to inject on every combustion cycle. Over time, the sensor becomes coated with oil mist, sticky dust, or residue from oiled air filters. Once contaminated, the internal thermistor can no longer accurately sense the true temperature of the incoming airflow. The result is a reading that's artificially hotter or colder than reality, causing the engine to run slightly rich or slightly lean all the time. This leads to a subtle but constant loss of power, increased fuel consumption, and in some cases light detonation in very hot climates. Technicians routinely find that careful cleaning with electronic cleaner, without touching the sensitive element, restores fast sensor response and stabilizes the air-fuel mixture. But there is another temperature sensor that controls something even more critical: the temperature of the engine's own heart. Number 6. The Engine Coolant Temperature Sensor. The coolant temperature sensor is one of the most influential sensors in the entire engine management system, even though it's rarely suspected. It tells the ECU how cold or hot the engine itself really is, and the computer bases many critical decisions on this single input. During cold starts, the ECU enriches the mixture, increases idle speed, and adjusts ignition timing based on coolant temperature. As the engine warms up, those strategies gradually fade out. When this sensor becomes coated internally with corrosion, scale, or sludge from old coolant, it begins to report incorrect temperature data. The ECU may believe the engine is still cold when it's fully warm, or already hot when it's actually cold. The result is excessive fuel consumption, rough idle, hard cold starts, cooling fans running at the wrong time, and long-term engine wear caused by improper fueling. Many engines that seem to have complex drivability issues are restored to perfect behavior after replacing or cleaning a faulty coolant temperature sensor. And yet, there is still one sensor left that almost nobody ever cleans, even though it quietly causes some of the most expensive problems of all. Number 5. The Vehicle Speed Sensor, VSS. When the speedometer needle starts jumping around, the transmission begins making strange shift decisions, or the cruise control randomly shuts itself off. The silent culprit is often the vehicle speed sensor. This sensor is usually mounted on the transmission housing or the differential, and it generates electrical pulses proportional to the actual rotational speed of the wheels or the transmission output shaft. What's really happening is that each of those pulses is converted into data the ECU uses to know how fast the vehicle is moving, when to upshift or downshift, how to manage fuel cut during deceleration, and when to activate systems like cruise control and traction logic. When the sensor becomes contaminated with oil, road grime, metallic debris, or sludge, its signal becomes distorted. Pulses arrive incomplete or irregular, and the computer may believe the vehicle is moving faster, slower, or even completely stopped while it's still rolling. In real-world diagnostics, technicians frequently find that simply cleaning the VSS, removing metal particles stuck to its magnetic tip, and flushing the connector with electrical contact cleaner restores a stable signal and eliminates erratic shifting that many drivers mistake for serious transmission failure. But there is an even more critical sensor, one that listens to the inside of the engine like a high-precision microphone. Number 4. The knock sensor. Bolted directly into the engine block is what is essentially a microphone that constantly listens to every combustion event inside the cylinders. This is the knock sensor, designed to detect specific vibration frequencies caused by abnormal combustion or detonation. What's really happening is that this piezoelectric sensor converts mechanical vibrations into electrical signals that the ECU analyzes in real time to determine whether the engine is beginning to knock due to low-octane fuel, excessive heat, or overly aggressive ignition timing. When knock is detected, the ECU reacts within milliseconds, retarding ignition timing and slightly enriching the mixture to protect the engine. The problem begins when the sensor becomes coated with dirt, corrosion, baked on oil, or is installed with incorrect torque. Its sensitivity drops, and it no longer accurately transmits those critical vibration signatures. The outcome is dangerous in two ways. Either real detonation goes undetected and the engine operates on the edge of damage, or false signals force the ECU to constantly pull timing, robbing power and making the vehicle feel heavy and sluggish. Simply cleaning the mounting surface and connector and reinstalling the sensor with proper torque often completely transforms engines that feel worn out or underpowered. But there are sensors that don't protect the engine. They warn you only when it's almost too late. Number 3. The oil pressure sensor. The red oil pressure warning light on the dashboard is one of the most feared alerts for any driver, and behind that light is usually a small pressure sensor that receives very little attention until something goes wrong. This sensor is threaded into an oil gallery in the engine block or cylinder head, and its role is simple but critical. Detect when oil pressure drops below a safe threshold. Internally, a diaphragm or pressure-sensitive element deforms under oil pressure, opening or closing an electrical circuit, or generating a proportional signal in more advanced systems. Over time, the sensor's inlet passages can become clogged with sludge, varnish from burnt oil, or debris, forming a restriction that prevents real oil pressure from reaching the sensing element. In that situation, the engine may be running with dangerously low oil pressure while the sensor reports normal readings, or the opposite, triggering false warnings due to slow and erratic response. Shops have documented engines showing perfect pressure on the dash, while an external mechanical gauge reveals critically low values. That's why cleaning or replacing this sensor during major services can be the difference between a protected engine and one heading toward catastrophic failure. But there's another seemingly harmless gauge that lies more often than most people realize. Number 2. The fuel level sensor. The fuel gauge feels like a minor detail until the day your vehicle stalls on the highway while still showing a quarter tank. Behind that misleading needle is the fuel level sender, a sensor that lives submerged inside the fuel tank and is almost never cleaned or inspected over the entire life of the vehicle. This system uses a mechanical float attached to an arm that slides across a variable resistor, changing electrical resistance as fuel level rises and falls. What's really happening is that the instrument cluster or ECU converts that resistance into the fuel level reading you see. Over the years, the resistive contacts oxidize, varnish from low-quality fuel builds up, and dirt deposits create false dead spots. The result is gauges that bounce around, get stuck at half-tank, or respond very slowly after refueling. In specialized shops, these modules are removed, the resistive tracks and contacts are carefully cleaned with proper cleaner, and float movement is checked for smooth operation. Many complaints about excessive fuel consumption actually begin with a lying fuel level sensor. But none of these sensors matter if the nervous system that connects them is failing. Number 1. Sensor connectors and wiring harnesses. In countless complex diagnostics, hundreds of dollars are spent replacing sensors that appear defective, when the real culprit isn't the sensor at all, but the connectors and wiring harness supplying it. Every sensor depends on 3 fundamental things: correct power supply, solid ground, and a clean signal path back to the ECU. What's really happening in millions of aging vehicles across the United States is that vibration, moisture, engine heat, and minor impacts slowly degrade wiring, pins, and terminals. Green corrosion forms inside connectors, intermittent contact develops, wires break internally under intact insulation, and grounds loosen and reconnect with every bump in the road. Scan tools show fault codes pointing to temperature sensors, oxygen sensors, position sensors, or pressure sensors, but in the shop, technicians notice that simply moving the harness causes the problem to appear and disappear. What most drivers never see is that a thorough cleaning of connectors with dielectric cleaner, correcting ground points, repairing pore splices, and properly securing the harness can eliminate electronic ghost failures entirely. That's why experienced technicians always inspect wiring and connectors before condemning an expensive sensor, because very often the problem isn't the component itself, but the path that carries its information.